Okay, so here is yet another real-world situation in which we are going to use our calculus skills to get the best out of the situation. So we are going to build a box with an open top from a piece of cardboard that is 3 feet by 3 feet in dimension. So you could imagine you've got a piece of cardboard 3 feet by 3 feet. And now we're going to construct a box from this piece of cardboard, specifically an open top box, by cutting a square from each of the 4 corners and bending up the sides. So imagine this. Imagine from each of the 4 corners, you cut out a square. Well, if you did such a thing, then removing that square, you could take the material that was left over, and if you bent up the sides corresponding to where the corners were cut out, you could yield yourself something shaped like so. And this would be a box with an open top, and well, you could imagine if you cut little tiny rectangles, the box wouldn't hold a lot of stuff because it'd be so thin in terms of its height. But if you cut too large of squares, you could actually remove all of the material from the piece of cardboard. So if you cut the squares to be like 1.5 inches a piece, you'd have nothing to fold up to make a box. So cut the squares in the corners too small, you don't have a lot of volume in your box. Cut your rectangles too big, you have no volume in your box. So maybe there's a sweet spot in between, and this is actually exactly what we're trying to do. So we want to find the dimensions of such a box to yield the largest volume. So right away, whenever you read the problem, it says we're looking for the largest volume. And you know then, we are looking for a volume function. Once we find our volume function, what we then need to do is just use calculus to find the critical points and test. Because we want to make sure that we've got a maximum and not a minimum, because, well, shoot, that would be misleading, of course, if we stumbled upon a minimum. So now, one question. How are we going to compute the volume of this box? Well, like any box, the volume is just length times width times height. And now the question becomes, well, what is the length? What is the width? What is the height? Well, that's going to depend on how big we make our cut, right? Our cut could vary in size. If we cut tiny rectangles, we'd have different measures than if we cut very large rectangles. So the squares that we're cutting from the corners of our figure are going to possibly vary in length. Let's call their measure x. Because my claim is that once you call that x, you can actually nail down every dimension on your box. Because you see x, whenever you fold, is precisely now the height of your box. Your box is going to be as tall as your square cut was wide, because the width of that square cut is going to be folded up, and that's precisely your height. Okay, but that doesn't describe the other 2 dimensions of your box. How big is the box in terms of length and in terms of width? Well, you can also see that from the picture as well, right? Because this measure here is just the width of the box. Now, while the width of the original piece of cardboard was 3, the width of the box is not 3. 2 x's have been taken away. So the width is 3 minus 2x. And now, if you think about it, the depth of the box, the length of the box, is also going to be the exact same value, right? Because we were using a square piece of cardboard, cutting out squares. So the measure within the box from front to back is going to be the original width of the cardboard, 3, take away 2 x's, 3 minus 2x. But now you see, we can compute the volume of our box in terms of our variable x, in terms of how big we make our rectangles. So length, 3 minus 2x. Width, 3 minus 2x. Height, x. And now you can run the numbers on that and FOIL to compute the volume function directly. Okay, let's see. FOILing, we have a 9 times our x, that would be 9x. Minus 6x, that's minus 12x, but that's multiplied by another x, minus 12x squared. And then we have plus 4x squared times x, that's plus 4x cubed. Here now is our volume function. Whew. We've done all the work to process what was going on in the problem to now get to the point where you would have had a question on your last test that you can run through all the calculus to solve. How do you find where the largest volume is? Now we just need to maximize. Take first derivative. 9 minus 24x plus 12x squared. That can be factored. I believe I can take a 3 out of that. And that's going to be 3 minus 8x plus 4x squared. Ooh, that's going to be maybe tricky to factor. Since that's going to be tricky to factor, I almost want to use the quadratic formula to find the x's corresponding to where this solution is 0. Maybe that could be factored, but yeah, let's just assume that it can for now, and let's just find the x's by the quadratic formula. So x is going to be negative b, that's 8, plus or minus the square root of b squared, that's 64, minus 4ac, that's 4 times 12, over 2a. A is the coefficient of x squared, that is 4, so the 2a, 8. 64 minus 48 is 16. This is actually going to work out fairly nicely. Square root 16 over 8, which is 8 plus or minus 4 over 8, which whenever you boil this down, in the positive case you'll have 12 over 8, and in the negative case you'll have minus 1/2. Would that just be positive 1/2? Yes, it would. Because, well, in particular, let's just be very direct about this. 8 minus 4, that's 4 over 8, 4 eighths. So 12 eighths and 4 eighths are the two possibilities, or simplified, x equals 2/3 and x equals 1/2. 3 halves, how about that? Whew. X equals 3 halves and x equals 1/2. So now, we've got to look at our volume function. We have x equals 1/2 and x equals 3 halves as critical points. And now we need to test on every side of these points to see whether the function is going uphill or downhill into these points. And to test whether the function is going uphill or downhill, we use the first derivative. And left of 1/2 is 0, and in between 1/2 and 3 halves is 1, and over here is 5. I don't know. I'll just pick something that might be telling in terms of its value. Plug in 0, what do you get? Plug in 0 to our v prime function. We'll get 3 times 3. V prime of 0 is 3 times 3. Well, that's positive, and the function's going uphill. So it feels like x equals 1/2 might be a maximum point, but to verify this, we're going to have to compute what the slope is between 1/2 and 3 halves. So to do this, plug in 1 here. This is going to be 3 times 3 minus 8 plus 4. That's what, 3 times minus 1. 3 times minus 1, that's a negative. And the function's going downhill. And hey, we've already got validation of the fact that we've got a local max here. What about the x equals 3 halves? Well, go to the right of that like 5. V prime of 5, that's going to be 3 times 3 minus 40 plus 100. So that's going to be 3 times something positive. That's going to be positive. And well, here we go. We've got a picture of the situation. Local max at 1/2, local min at 3 halves. Find the dimensions of such a box. Well, from the fact that we had a local max at x equals 1/2, we know one of our dimensions is going to be 1/2 a foot. What are the other dimensions going to be? Well, each other dimension was 3 minus 2 times x. Well, if x is a half, 2 times x is 1. So removing each of those squares of a half a foot leaves 2 feet in each direction. So a half foot by 2 foot by 2 foot. We found the local maximum point, and the local maximum point is going to be where we yield the largest volume. And now, as I say that, and if you look at this, you might think, but, Dr. Bly, this function is increasing to the right of x equals 3 halves. So, in fact, while x equals 5 has a positive value for the slope and hence a very large volume measure, x equals 10 would have an even larger volume measure, and x equals 30 a larger volume measure yet. We should just pick x equal to be as big as we possibly could. But note, with respect to the original problem, we couldn't just pick x to be as big as we possibly wanted. In fact, the largest that x could possibly be is 1.5 feet in each measure. So in fact, this region that lies to the right of 3 halves is able to be discarded because it's not physically possible to cut rectangles, or squares rather, from each corner of your piece of cardboard of any dimension bigger than 3 halves. And in fact, the 3 halves is what we observed initially was where the volume would be 0, and that is the minimum possible volume, which makes sense. The x's that are to the right of 3 halves don't make sense within the context of the problem, in spite of the fact that mathematically they are values along this function. But with respect to the function of interest and the problem of interest, we found our maximum point. And the biggest dimensions we could, the biggest amount of volume we could get from our box would be if we did a half a foot by 2 foot by 2 foot. Pretty cool.